Electric motors basic. Electric motors is part of our everyday's life. We used to have rotational movement helping us since ages. This is a windmill which was used long time ago in mostly in Amsterdam. If you will go, you will find a lot of them using the air, and below this you will either find one oil extracting a machine or some electricity producing machine. This is a well where we are having a rotation to throw the bucket down. This is, I can say, this is an old version of the pump maybe. But an even older version of the pump is this Archimedes screw, where this flow of the river is generating the rotation and the water is going through up. So, and then it goes to reach to some height, and from there it travels to long distances. So this was old way of moving the water from one place to another. This is called Archimedes screw. Now rotation is very important. That's what the motors are for. So what motors do? Motors generate rotation, and there are many different types of the motors. Many DC, AC, reluctance switch motors, medium voltage, many of them. But why we make a lot of motors? Based on the different demands we have. Some demands ask us to have very high speed, but the loads are very low. Some applications ask us to very low speed, but the load is very high. For example, I usually give an example of the elevator. If you stand in an elevator, it goes very smoothly and take up to 150 kilos. So that means that this motor is running at a very low speed but very high load. But in the pump is rotating at 3560 rpm, and usually the amount of the water which we are using now in our daily houses is 10 meter cube per hour or 20 meter cube per hour. This is the standard ranges of the pumps in our house. So the different demands usually ask us to have different motors, and that's why we have many kinds of motors. But the most used or economical possible motor in the world and used nowadays is squirrel cage induction motor. This induction motor or squirrel cage induction motor is the motor which we are going to talk about today, and this is the motor which you will find in all the pumps, all the exhaust fans, all the fans in the world, all the HVAC compressors, everywhere in the world. Majority of the time you will find squirrel cage induction motor. So this is very relevant and very relevant to the pump industry as well. But most of the concepts will remain same. Sometimes few things will vary, but the motor concepts remain same. Now the concept of induction motor was given by this gentleman, Nikola Tesla. He gave this concept in 1888 that we can make a small device which can generate a rotational. This is a rotational movement with the help of electricity. This was electricity, and these was all the wires, 6 wires of electricity going inside. So what he was mentioning, that you can create a rotation motion with the electricity. That time, creating an electric motion, creating a revolving motion with electricity was something very new. And today's motors are very similar to the same design which is shown in this patent in the 1888, which is we have some electromagnets, we have some rotor which is rotating and generating the rotational motion. So this is what we are going to talk about today, how this operation works, what is the principle behind this operation, what are the electromagnets, how the electricity operates on this motor, what is the rotation generated, what are the characteristics of operation or of the rotation, because rotation also have meaning that fast rotation, slow rotation, fast rotation with heavy load, low rotation with heavy load. There are some characteristics of the rotation as well. So this is what we are going to talk about. The agenda, as we discussed, electric motor basic and its output, standard for AC motors. This is very important because there are more than probably 5,000 manufacturers of the motors. So how you will know which manufacturer is good, or how you will know that which manufacturer will motor you should buy, because one manufacturer can vary from a different one. But these standards help us to identify or differentiate between different motors, because all the manufacturers are using the same standards of manufacturing. Now in the world we have two major manufacturers, two major standards. You might can guess it already. The two major manufacturers or standards are European and American. So the debate of which one is better is never ending. I would say both are very good. There is no difference in both of them. Both are designed for their own purposes, and both are good with their own benefits, and the difference is very minimum. Sometimes it's just the difference of saying meter and feet. At the end of the day, both are same. There is nothing called the distance. At the end is the same thing is with the motor. At the end you just need to create rotation, you don't need to create anything else. Then we'll talk about motor protections, how we can protect the motor to increase the life of the motor, because this is what we want to increase. We want to increase the life of the motor. Also we want to protect the people, because this is an electromechanical machine, which means it is taking electricity and converting it to a mechanical movement. So we need to make sure that the operators which are working with this machine are also safe with this. Then we'll talk about the starting methods, how we can start the motor, what are the different methods, and which one, why we need, first of all, why we need one, and if we need one, what are the good starting methods. Now this is the basic concept. Earlier we used to have some animals which were rotating around and around and around, and this job of lifting was done. But now this is all changed to motors. Now motors are the ones who do this rotational job. So what we actually want is rotation. So what are the characteristics of rotation? What actually we mean by motor torque and the power? Because what we usually know is a motor of 5.5 kilowatt. We usually don't know many things after this. But what is the meaning of 5.5 kilowatt? What it actually do 5.5 kilowatt? So this is what we are going to talk about. So what motor do? Motor generate the torque. The torque is the twisting force. The twisting force means that this will rotate around this axis, and you can put some this motor which is generating, so the torque will able to rotate or apply some force on it. So the basic idea or the basic definition of torque itself is the force applied to a certain distance. This is the torque. I mean, this is the pivot point, this is the radius, and this you are applying the force. But this is you applying force, not motor applying force. But when we talk about in terms of motor generating the torque or motor generating the power, it is the very same, because motor, if you see here, motor will also generate the rotational torque, and motor will also rotate, because in this one it is also rotating with some radius. And motor will also apply some force, because if this is the pump and this is the bare pump and you try to rotate it with your own hand, what you need to do around this shaft, you need to push it. If you push it, the shaft will rotate a little bit. The same task will be done by the motor. So what motor do? Motor generate the torque, the twisting force, to the shaft of the pump, and then the pump start rotating, or the motor generate to any load to which it is connected. So the power of the motor is defined as this: torque it is generating, or which torque is the radius into the force, and W is the rotational speed. how, or you can either say RPM, or this is minute or rotation per second. Actually it is in the formula it goes by second because this is metric formula, but in normal world we talk about RPM. So that means that a motor power is defined as, if we say 5.5 kilowatt, is defined that it can give some power, which is, I will come to that, what power is. This is in Newton meter. It can give you some power at some speed. The speed is also very important, because if the speed changes, the power is also changing. And if you can see, the torque and the speed are inversely proportional. That means if you increase the torque, the speed reduce, or if you want to increase the torque, you have to reduce the speed. Now I will give you a very simple example in normal world, like car. When we are in a smaller gear of a car, what we have more power, but we have less speed. But if we are in fifth gear, with what we are giving more speed. Rotational speed is more, but the power which the motor is with the power with the car is required or generating is less, or with the car is required, the power is the car required is less. So these both are inversely proportional to each other. So this is the same scenario. If but the sum of them will remain same. That means if you will increase one, the other will reduce, but the total generated power will always remain same. That is the reason, if you are going uphill in your car, if you are going above the hill, you will slow down your car, or your car will automatically slow down, or you will put your car in a lower gear. And if you are going on down the hill, you will not put in a lower gear, you will increase the gear, because you don't need too much power. So the motor output is the force which it is providing at some speed. Now the force is what? Newton meter, and the speed is RPM. So these are the two characteristics of the motor which you can get on the motor data sheet. How much power it can apply on the motor shaft, and at what speed that power can be applied. Now if you for example, if you increase the speed and keep the power Newton meter same, that means this power will increase. But if you decrease this and increase this, both inversely proportional to each other, the power will remain same. Now how to calculate them, because this is something which is very important to calculate. Before we go for the calculation, in real world, the rotational power of this wheel rotating from this point to this point, or from this point to this point, if this horse is taking 1 second, that means this rotation is generating in 1 second, and it moves 550 pounds of this mass to 1 feet. If we combine, if this horse did all of this task in 1 second, then this horse generated 745.7 watts, or 1 horsepower. This is the real world meaning of horsepower. That what is the when we say 1 horsepower, what exactly is 1 horsepower? How we can differentiate in real world 1 horsepower? Now, for example, if this horse did the same movement of moving 1 feet of 550 pounds, but in 2 seconds, will this be 1 horsepower? No, this will be 0.5 horsepower, because it is taking double the time of doing the same thing. But what if it take 1100 pounds to 1 feet in 1 second? Now it is 2 horsepower. So this is how we derive how much power it is generating in real world. But in real world, if I take this motor and this is the shaft, and if I start calculating how much power it is generating based on how many horses are required, it is nearly very difficult. For that reason, we use electrical parameters to calculate the motor kilowatt. So the electrical parameters are much simpler. How we can do it for three-phase motor, for example? We know the voltage we are applying to the motor. We know the current we are applying to the current motor is consuming. We are not applying actually. Current is the characteristics, is the power which the motor consume. If you are doing more task, or if your motor is running on a higher load, it will consume more current. Voltage will always be constant. Cos theta is the power factor which changes based on the current. This is the constant, this is the constant. The result of this, you will get kilowatt. This kilowatt will be equal to this change, this equation. You can see if 1 kilowatt, if I can say 1 kilowatt, that will be 7.7 this will be 1 kilowatt will be 746 watts horsepower. 0.76 horsepower. If I say 1 kilowatt will be 0.76 horsepower, and the same will continue. So to measure the power coming out of the motor, what we do, we see how much power, how much current is going inside the motor, how much current the motor is consuming, what voltage we provided, we put it in this formula, and we calculate how much power this motor is generating. Now from the kilowatt, how you can calculate the torque, because in the beginning if you remember, I talked about the torque is something which is the force which is generated. Now this is very simple. If you know power is equals to torque into W. Torque, if I want to calculate the torque will be P over W. Power will be kilowatt. If I will keep it, power will be kilowatt. This will be 2 pi R. So this will be my 2 pi R. Now to keep it to keep 2 pi, power will be, I will put it in kilowatt. 2 pi will be 3.14, but my radius was radian per second. To make it what we say minutes, I need to divide this by 1 by 60. So this will go up. So the total function will become 60 multiplied by 1000 to make it what? To make it watts, because kilowatt is not the standard is the watt. So 1000 divided by 2 into 3.14. Once you will multiply all of this, you will come to this 9550. So if you want to generate how much Newton meter power is generating out of the kilowatt, for example 5.5 kilowatt motor, how much torque will be generated by this motor, you just multiply this 5.5 kilowatt with 9550. This much Newton meter power will be generated by this motor. But do you really need to calculate this every time? Actually no. This is the standard motor datasheet given by the motor manufacturers. If you see here 8.2 Newton meter, the power is already given to you. This is 16.4 Newton meter. The torque is given to you. This is 3 kilowatt. This is 3 kilowatt. The current is given. The maximum current is given. The rated current is given. The rated current is the current at 3 kilowatt. The starting current. All of the factors are given. One thing to notice here is, as I said in the beginning, if we reduce the speed in half, we will double the torque. You see here 3470 is the speed here. I reduce the speed to 1730, which is half. I double the torque. 8.2 torque here, 16.4 torque here. Why? Because this is 4-pole motor. I will talk about pole in a while, and this is a 2-pole motor. So in 4-pole and 2-pole motor, the kilowatt is same, but the work done is different in terms of speed and the torque. So the speed and the torque here is, the speed is high and the torque is low. Here the speed is low and the torque is high. So in pumps perspective, if I talk about pumps, this motor will be used for the pumps which are designed for high pressure, because if I increase the speed, I will increase the pressure, and if I reduce the speed, I will reduce the pressure. But these pumps are used for high flow, because for higher flows we can use slower speeds, because we do not need to generate high pressure. Whenever we need to generate high pressure, we will go to higher speed. There are few pumps which goes up to 5400 rpm to generate up to 40 bars. So these are the differences, or these are the applications, or these are the reasons what we choose. So when we say we need 4-pole pump, why we will go with 4-pole pump? Because usually the flow is very big. So when we will say, well, I need 2-pole pump, I will need 2-pole pump when my head is very big. So that are the differences when to choose 2-pole pump or 4-pole pump. So 2-pole pump are more efficient in developing the pressure. 4-pole pump is more efficient in providing more flow. So this is the comparison between both. Now coming to the basics, how the motor operate, going inside the motor. The motor operate in 3 steps. First we give the electricity. This is the incoming of the motor. Then the motor convert electricity to magnetic energy. Then magnetic energy is the energy which converts the electric energy to mechanical energy. To mechanical energy. So from electricity to mechanical energy, the thing which helps the both is magnetic energy. Supply we know very well. This is the electricity which we get in our house, either single phase or 3-phase. So we know this very well. Load, we just discussed this. This is the rotation, torque into rotational speed or kilowatt. This both things, both this and this we know very well. We need to learn more about magnetic energy to understand what is magnetic energy and how it helps electricity to rotate something. So what is magnetic energy? Magnetism is a concept. By default, the real magnet is a material and a concept which can physically attract or repel a substance in real life. That means if you have 2 magnets, magnet 1 and magnet 2, and you bring 2 poles, south pole and south pole of both magnets in front of each other, they will create a physical force to push them apart. This is a physical force coming out of a material. This is a natural material of magnet. Then if you bring across each other 2 different poles, if you bring south pole and north pole in front of each other, they will attract each other. That means again they will bring a physical force. Now here physical force is very important. Why? Because what we actually need, we need to generate a physical force of rotation. This is what we need at the end of the day, a physical force of rotation. This force we will put it inside a pump to take water, or this force we will connect it to the fan to take air. This force will connect it to the elevator to move the people. But what we need is a physical force. So what magnet is doing is giving us a unilateral unilateral in one direction, horizontal or vertical, depend on how the magnets are placed, horizontal or vertical forces either pushing or pulling each other. Now, are the motors made of these magnets? Well, it will be not economically possible to make the magnets to make the big motors out of these magnets. Why? Because these magnets are natural material, and we need a very big magnet to make maybe one motor for your elevator. Maybe your motor for an elevator will be bigger than your elevator itself because of the magnet inside it. For that reason, what we come is electromagnetism. Now electromagnet is just behaves exactly like a magnet. In this we have one conductor, which is a copper cable, or could be any cable, tin cable or silver cable. Usually the used one is a copper cable. A copper cable, and then a flow of current is passed through it. How the flow of current is generated? The flow of current is generated by giving them difference of potential, by connecting it to a battery, or you can say this is my battery with plus and minus. I connect this, or connect it to a power supply or anything. So the thing, whenever I give a difference of potential here, for example, I give here 5 volts and I give 0 volt, the electrons will start moving. Once the electrons will start moving inside a conductor, a wire, it will generate the magnetic field. This magnetic field is exactly the same as the magnetic field which we just saw in the permanent magnet. That means that if I have 2 cables, for example, if I have another cable here and another current is passing through it and another electric flux is generated, this flux and this flux will interact with each other, and this cable will either push or pull. This unilateral force will be generated. So what we do with electromagnetism, we generated a artificial magnet. Now in artificial magnet, if I remove this, for example, if I remove this, let me just remove all the writing also. Yeah, if I have this small battery or power source and the current is moving, this is an electromagnet. But if I remove this voltage source, this will no longer be a magnet. This will just become a small copper cable. So now what we have achieved with electromagnetism, number 1, we can make and stop a magnet. So on our choice, we can either make a magnet or we can not make a magnet. Or in other words, the second thing which we have achieved is direction of north and south, or direction of rotation, or direction of magnetic field. If the flow is the current is flowing in this direction, the north and, for example, north and south will be in this side. But if we reverse the direction of the flow of current, the north and south will also change the direction. That means that if I have, okay, I'm discussing the same thing here. If I have this copper wire which is having a lot of turns here and coming out, now if the current is going inside this is my north and this is my south. But if I change the direction of current, that means that now the direction of current, rather than this, I close this and I change the direction of current to going inside here and coming outside here, then this will no longer be a north, this will become a south, and this will no longer be a south and this will become a north. That means what I have achieved, I can not only make this magnet on my will, but also I can change the south and the north of this magnet. How it will help me in the coming videos, in the coming slides, you will understand how this change of south pole and north pole will help us to make an electromagnet, to make a motor. Now this is a small video which is explaining how electromagnetism work in real life with some batteries. Just have a look. Oops. So what we have here is just one battery, one coil, and this become a magnet. Because the current is always flowing through this loop, always. See, it is plus and minus, very simple magnet. Now here there are 3 different magnets. What you can see here, they have 3 different magnetic forces. One have less, one have more, and one have even more. why it depends on this? Why it have more? Because the number of turns, or the number of amount of copper inside this electromagnet was way more than this electromagnet. Although the thickness of this copper wire was more, but it does not depend on the thickness. It depends on the amount of the turns. The more turns you have, the stronger electromagnet you will get. Now, if you see here, it is giving some voltage. As it starts reducing it, it starts losing its electromagnetism as well. So this is the amount of the current going through this electromagnet. So if we increase the surface area, we can also increase the magnetism of the electromagnet. We just have the more surface area, so this becomes a bigger magnet than this. So just a small battery is strong enough that these two people cannot remove these magnets from each other. So this is how strong a small electromagnet can be. And this is, they are changing north and south. Earlier it was not attracting, now it will attract. And it will generate a strong force of attraction. So this is how electromagnets work, and this is the building block of our motors. Now how this electromagnet help us? How this electromagnet is in real life generating from a unilateral motion. Earlier you saw either a south and a south is repelling each other, or a north and a south are attracting each other, but this was always a unilateral force. But in motor we need a circular force. So what we do, we place the electromagnets in a circle 120 degrees apart from each other. So this is one static example. I will explain how they are placed, and then I will explain how this goes further. So this is the first south pole, north pole, south pole, north pole, south pole, north pole. This is the stator of the motor. The stator of the motor is the component which will not at all rotate. This will always be in stationary part, and the magnets on this, or the electromagnets on this part, will be always stationary. This is the rotor. This blue part is the rotor of the motor. This rotor is the thing which will actually generate what? The rotation, the thing which we actually looking for. Now what happens is that every given moment, if this given moment, this south pole is attracting this north pole is attracting this south pole, and this south pole also is repelling this south pole. So this is pushing this here, this is attracting this, and this is pushing this. This electromagnet is attracted towards this, and this electromagnet is pushing this towards this south pole. So this is pushed towards this is pushed towards this is pushed towards this is pushed, this is pushed. If you see here, all of them are pushed towards its next. So this will create a rotational motion. But you can ask me, what will happen if this south will come exactly in front of this south, and this north will become exactly in front of this north, and this south will come exactly in front of this north? What will happen after that? This motor will stop. Yes, you are right that this motor will stop at this point. So what we do actually, we always rotate this motion. We always rotate this electromagnetism or magnetic fields around this around in the stator. That means there is a rotating magnetic field in the rotor. And how this rotating magnetic field is, in the beginning I said you can change the north pole and south pole. So what I will do, once this will reach here, this south will reach here, and this south will reach this south. This is north, this is attracting. I will change this south to north and this adjacent north to south. Now these two will repel each other, this south will push towards the next one, and then this north, let me change my color to this. Yeah, okay. Now this north I will change to south, because already this south was earlier pushed and here it is south. Now this, when I remember in the beginning I said I can change the direction. I will change the direction of the magnetic field. How? By changing the direction of the current. I will come to that, how I change the direction of the current. But what is physically happening now, this north pole will become south, this south will become north, this north will become south, and this south will become north. Now when this next one will come, it will again push. So when this push will come, it will again take not the complete circle, but this again go to the second one and then go to the second one. Now this magnetic field is also rotating at a very high speed. This magnetic field is actually rotating at 3650 rotations per minute. That means I will come to that how I come to this figure, or how suddenly I said 3650. But just to give you an understanding that how the rotor is rotating inside the stator, is because there is a magnetic field which is always pulling these magnets. These are the small magnets inside the rotor, which are always pulling this magnet with it, because this magnetic field around the stator is rotating. So what is happening? This pull and push is happening between this and this. Now currently, if we go to the earlier scenario, this south is attracted towards this north. But what happens when this south attracted towards north, it attracts and come towards here. By the time it comes here, it was changed to south. When it changed to south, it pushed this south towards this next north. By the time it will go to the north as attracted, what will happen? This will change to a south, and then this is how it will start generating the rotational motion inside the rotor. And this rotor is free to move. You can easily rotate with your hand. So because of this very low friction, this magnetic field rotating around the rotor will attract the rotor along with it. So this is called the induction. This is called the squirrel cage induction motor. But how this different parts are working? Now the question is how I am able to change this south to north and north to south. I said earlier that I can change the direction of the current. How I can change the direction of the current? Here comes this alternating current. I said I will be most of the motors used in the industry are squirrel cage induction motors. They are squirrel cage induction AC motors. That means that what we give to them is this waveform. So when the current is going in this direction, the current is actually going in one direction only. When the current goes in other direction, when the current is in this phase, the current is actually going in opposite direction. This is the frequency or the waveform of the electricity which we give. This is the current waveform. That means that this will happen, or this is the voltage waveform. This will happen 60 times in 1 second. So this is in 60 hertz power supply, because this is in Saudi Arabia. This is 60 hertz power supply. That means in 60 time in 1 second, this going up and down will happen 60 times. That means this north and south, which is changing because of the flow of the current, will change 120 times. Or you can say there will be 60 south and 60 north in 1 second. In 1 minute, you just multiply 60 multiplied by 60, how much it will come? 3600. So this is the speed, at what speed we are actually changing remember I said this number 3650, this 50, you can say magnetizing does not happen. There are some losses here, so you can say 50 turns are lost in the losses. But because of this change which we are changing inside this stator, the magnetic field change, the rotation of the magnetic field, this is happened because we are going in 60 hertz. But in 50 hertz we will have 50 into 60, because this waveforms, we have only 50 waveforms in 50 hertz. So now we get that how we change this south and north. That's very good. Whenever we change, we get the rotational. Whenever this is south, this is north, it will attract it, this will move, and by the time it will come here, this will be automatically north, it will push. And the same thing happened to all of these magnets, and it will start a rotational motion. Now let's take an example, a very well arranged magnet. In this case, I will say there are three magnets. A is a magnet, and 1 is the part 1 and 2 is the part 2 of that one magnet, which is north and south. B is a magnet, C is a magnet. 2 and 1 are the two parts, 1 and 2 are the two parts of C, and 1 and 2. In between, instead of a rotor, what I put is a real magnet for you to understand. Currently, just understand that this is a real magnet. So what happens is, this is my waveform, and I take 3 times. This is time number 1, this is time number 2, and this is time number 3. In time number 1, if you can see here, this is south and this is north. So this south and this north, they will attract each other. So this is attracted towards this will create this motion. Okay, this is time 1, and this south will be attracted towards this north, because this north and this north, so this already generated this motion, so this will be attracted to this, so this will move here. But by the time it reach here, in just this small split of a second, because this one wave, which this blue wave you can see, this one wave will come in how many times? 60 times in 1 second. Now we have 3 phases of this. One electromagnet is connected to one phase number 1, which is this blue phase, you can say blue phase. The red one is connected to the phase this B2, and the 3 phase is connected to this. That means that every electromagnet have its own phase. Now at this given point, if you can see here, the red one is 0. That means this B is 0, the phase B. So B2, this phase B is for B2. This is 0, that means very near to 0. It does not have any electromagnetism at all. Why? Because it is actually going through a phase of this. That means no current is flowing through it. Phase A, which is this A1, is having north at the peak, and phase C, which is also having north, or having one north and one south at the peak. That means that A1 having one north and one south, and C1, which is this phase C, having one north and one south at a peak. At the time we will reach here, what will happen? Our rotor already rotated to this, so it moved from here to here, so this is the direction now. But if you notice here, this north moved from A1 to C2, and this north from C2 to B1. Why? Because at this time number 2, what is 0? Phase 1 is 0. If you see here, there is no electromagnet here anymore. All the electromagnet is gone. Now we have N, which is coupled with this south, moved to the next point. Why? Because this electromagnet is now moved to this point. Why this movement? This movement also take this magnet, this permanent magnet with it, which is at point 2. At the same time, this caused this movement, and the north pole, this caused this movement. North pole, again the same thing is happening. The south pole is attracting this north pole with it. Earlier the south pole was here. Now if you see here, it is generating this kind of pattern. This is pattern number 1. This is north pole, south pole. This is north pole, south pole. In next time, what will happen? it will be here, south and north, and then north will move here and south will move here. So what you see is this rotation. So this is how it is generating. At third point, you will see, at third point, what is 0? Phase B is 0. Sorry, what is at third point? Okay, usually phase C is approximately is the least one. It's not, the time 1 and 2 3 are not taken at 0 exactly. If I take point 1 and 2 3 at 0, this is the phase A 0, this is phase B 0, this is phase 3 0, but they are not taken just for the example. But if you see here, this against south is attracting this north, and this north is attracting this south. If you see here, this is first rotation, this then change to this rotation, this then change to this rotation. Now this is actually rotating in this. So at the end, just by changing the current going inside the electromagnet, I am actually generating a rotational movement. So this is how a AC motor is moving the magnetic field around it. So this magnetic field is taking the electromagnet with it, and because of this attraction between these two north and these two south and this north, and these two north and this south, whenever these two north will move to the next one and these two north will move to the next one, this motor will start rotating. It's a bit complicated to understand. I would suggest to see some videos online, to see some animation. I will also show you some, then it will make, I will also share some links with you, and it will make some sense if you are having difficult time to understand. Then some components of the motor. I will just go back to this. This is how your motor looks like in real life, and these are the components of the motors. Now major components of the motor is this squirrel cage, which you can see here, this windings, the cables, this is the rotor which I was trying to show you, which will become a magnet. This is the place from where the terminal board, from where we will give all the electricity to the motor. There are a lot of other components which we will discuss which we will discuss later in some other time, in some next slides. And this rotor is actually rotating. If you notice here, there are two bearings, this one bearing and this one bearing. That means this rotor is attached between two bearings, and these two bearings are making sure that the rotation of the rotor is as free as possible. And secondly, all the rotational movement will be happening in these windings. I will come to that how these windings are working. Now this was all the components of the motors. Now coming to the induction part. If you remember, I was talking about this part being a permanent magnet, but it is not mandatory to have this as a permanent magnet. Why? Because we can use a concept called induction. The concept of induction is that if you take a real magnet or a magnet and run it across the cable, it will generate the current through it, and this generated current will again create its own magnet. So what you are doing in the motors, rather than having this permanent magnet, because of the rotation of these magnets, remember I talked that these magnets are rotating, or this north and south is rotating. This rotation will generate, if we keep a piece of metal inside it, which we call in real world a rotor, and this is how a rotor looks like. And if you see a rotor is nothing else than just a metallic bars, these metallic bars. And if I rotate a magnetic field around it at a very high speed, this rotor will generate current, and once this will generate current, it will generate its own magnetic field. This magnetic field will interact with each other and start rotating. That is the reason these motors are called asynchronous motors. Why asynchronous motors? So this is something called synchronous. There are motors available in synchronous, because in synchronous motors we use actual rotor as a permanent magnet motors. There are benefits of that, and their efficiency of the permanent magnet motor is very high. But permanent magnet motors are expensive and difficult to make on a bigger kilowatt. The motor which will use the concept of induction are called asynchronous. Why asynchronous? Because the speed of this magnetic field, this rotating magnetic field, will not be the actual speed of this rotor inside the pump or inside the motor, because few of the rotations will be required in the beginning to make this metallic or this rotor, which is this, to make this rotor a real pump or real magnet. Because once it will be a magnet, then it will interact with the magnetic field, and then it will start becoming a motor or a rotor. So this concept is very, very simple. If you can see, this is a magnet, and if you are pushing it, it generates a current. This generated current will in return makes another magnet. This is called induction, electromagnetic induction. So this is how it works. Just consider now that these are the electromagnets which are rotating around it very fast. This is the metallic bar. Once it will rotate very fast, it will generate an electric current inside it. And that generated electric current, what it will do? It will make its own magnetic field, and that magnetic field is going to interact with it. Now, how to calculate synchronous speeds? If you see here, I am writing synchronous speed. I am not writing asynchronous speed, because these are the speed of this magnetic field rotating. This is not the speed of the rotor which you will find in real life. So how you can calculate is 120 is as I said, remember I said in the beginning that we keep them 120 degree apart. So you can remember 120 into F is the frequency. So for 50 Hertz pumps, it will be 50 Hertz divided by pole. So number of poles, I will come to that. What is number of poles? So we can have 2, 4, 6 pairs. So we can have all even numbers, because poles are always in air or always in pair. So if we have 2 pole, 4 pole, 6 pole, so if we put these figures in this formula, you can get the synchronous speed. Synchronous speed, that if the pump rotor, that means this rotor part and this magnetic field is rotating at the same speed, then it will be 3600 rpm for 2 pole. But in real life, this is not 3600 rpm. This is something called 3650 or sometimes 3455. Why is that? Because this difference of this will be considered as slip. So the percentage slip is the characteristic of the motor, which is defined as how much difference will be there. IEC defined some standard defines some percentage of the slips. If you see here 1770, this is the motor speed, but by default it should be 1800. So 30 rpm was required to make first the rotor magnet. Once this is magnet, then it starts rotating. But this process happens throughout during the rotation. And this is the very simple formula of the synchronous speed. It is just the percentage. Synchronous speed minus the rotor. This is the actual speed at which the rotor is rotating, and synchronous speed. The motor nameplate speed which you will get is always the actual speed of the rotor. It is not the slip. It is not the synchronous speed of the motor. But if you are using permanent magnet motors, remember I told you permanent magnet motors are possible, in which the rotor is made of the real magnet, then your slip percentage will be 0. Why? Because your rotor speed will be this is equal to this, then this will be 0, and your slip will be 0%. So permanent magnet motors have 0% slip. That's why the efficiency of the permanent magnet motors are way better, because you don't need to spend a lot of energy in making this rotor a magnet, because this is already north and south and north and south and north and south, already a permanent magnet. So this is the benefit of having a permanent magnet motor. Now, number of poles. Number of poles is defined as how many number of north and south pair are available, how many magnets are available per phase. So this is 2-pole motor, this is 4-pole motor, this is 6-pole motor. If you see here, per phase, this is only one magnet, this is 2, and this is 3. So per phase 2 magnets are available, that's why this is 2-pole. But in this one, per phase, this is phase A1 is the phase, A1 is the phase. Per phase there are 4 magnets available. This is 1, this is 2, this is 3, this is 4. So this is 4-pole motor. 6-pole motor, per phase how many magnets available? 1, 2, 3, 4, 5, 6. This is 6-pole motor. So if you are seeing here, the speed of the motor is reducing as I'm increasing. See, as I'm increasing the number of poles, the speed is also reducing. If you remember, in my power equal to torque into rotational speed, torque was inversely proportional to speed. If my speed is reducing, that means my torque is increasing. In other words, having more magnets inside the motor give the motor a capacity to have more load. That means it can carry more load at lower speed. That means that the motor used in the elevator will be probably 8-pole or 10-pole. Why? Because you need very low speed, but you need high torque. You need to take more weight. Why it is able to take more weight? Because you have more magnets, more magnetism, more force, attracting force available inside the rotor. So that is the reason, or that is the concept of having more poles of the motor, or having different number of poles of the motor. So usually by default we have up to 12-pole motors. I in my experience I have never seen a motor above 12 poles. They are used in a very big flow. When the flow of the pump is very high, we usually use bigger kilowatt or bigger pole of the motors, because we don't need very high pressure. But in other words, in a motor concept, number of poles is defined as number of magnets per phase. So this is very basic definition of number of poles of a motor. And as the number of poles increase, the torque generated by the motor is also increased, but the speed of the motor decrease. That means the power remains same. Components we already discussed. Now coming to international standards. From now onwards, what we will discuss is all about international standard, the practical examples of all the standards and how they are applicable. NEMA standard is the standard which is applicable in Americas, and they are the NEMA MG1 standard. IEC standard is applicable in all around the world, including Saudi Arabia. In Saudi Arabia, usually both of the standards are available. So in oil and gas you will find NEMA. In oil and gas you will find NEMA standard more. In commercial building services and in commercial building and industry you will find IEC standard most. I will give a comparison by the end of this session, but both of them, if you compare with the cars, usually it fits perfect in my opinion. If you look at an American car, you will find a big, bulky, heavy car, and if you see a German car like Mercedes or something, you will find small, more agile and more to the point car, or you can say a car very well designed car, you can say. So this is the difference in the motor as well. In NEMA motors, they are oversized and they are having more, you can have more area of error in American motors, but in European motors the area of error is less. You have to design your system very carefully in order to run the system. So they are having a tighter tolerances. That is the reason IEC motors, compared to economically compared, the prices will be not very cheap, but slightly less expensive than American motors. American motors will be expensive than IEC motors, but we'll come to that comparison. So what are the standards, international IEC standards? These are all the international IEC standards applicable on any given motor. So when you will find a CE mark on the motor, that means that motor is complying to all of these standards which are defined below. We will go through some of those standards. I will send you these presentations. You can have a look on them. But these are all the standards to make sure that every manufacturer who is making the motor make sure that motor complies to this standard and can be interchanged. For example, you purchase a pump from one company, and you want to replace the motor with the motor, or you want to buy a motor from a different company, or you want to replace the motor from a different company. How you will make sure that the motor you will buy from a different company will come with the same standards, or with the same sizes, or with the same shaft size? This is what is defined by all of these standards. It makes sure the harmony between many different manufacturers available all around the world. So the first standard is the rotating duty cycle and ratings. These standards talk about how often or how long you can run your motor. So this motor, S1 duty type, is usually the motor with all the pumps. That means you can run this pump for 24 hours, 7 days a week without any stop. It is not required to stop the motor. It is not mandatory by the manufacturer of the motor to stop the motor. Whereas S2 means short time duty. That means that you can run it for 4 hours, but you need to stop it for next 2 hours to again run it for another 4 hours. So this is a short time duty. Then intermittent duty. All of these different duties are talking about how long or what type of a motor you can run. Now this type is S1 is always the best. No, it depends on the motor type or the application you are using the motor for. For example, this duty type S5, intermittent duty with electric braking. That means that you will be using the motor and your application is that you are stopping the motor also. Once your application is stopped, you are forcefully stopping the motor. Then there is intermittent duty with starting. That means that this kind of S4 duty motors are the motors in which that you will always have a high starting current. For example, a motor for a conveyor belt. Motor for a conveyor belt will start and stop and start and stop, but whenever it will start with a high starting current. So these are the different types of the starting current. But for the pumps, always motors used are S1 duty, and it should be S1 duty, because motors are designed to work for 24 hours a day and 7 days a week. There is no stopping or mandatory stopping required for the motor of the pump. Then the next one is the tolerance. Now tolerance is how much motor is allowed to deviate from the given on the motor nameplate. Now whenever you receive a motor with the nameplate. The nameplate define all the characteristics. The efficiency will be this, the kilowatt will be this, the voltage will be, for example, 380 to 405. Now these characteristics have some tolerances, some plus and minus variation. How much that be possible? As per IEC 60034-1, it says that the efficiency of less than 50 kilowatt motor shall not be less than 15%. For example, that if they are writing efficiency of 93% and you tested your own efficiency, it should not be less than 15%. And for machines, should not be less than 1 minus the efficiency. That is, you 1 minus this, and then the result should not go 15% lower. and then for 50 kilowatt it should not go less than 10%. That means that every motor which will follow this criteria, you can be rest assured that the efficiency which they are publishing in their data booklet will not be going below than these parameters. Power factor will not have a difference of 0.02 power factor to 0.07 cos. Will it be always the same which they are mentioning on the nameplate? No, because sometimes, usually motors below 50 kilowatt, they are not they are tested, and they are tested and they are marked. But with the passage of time, the motors always always reduce the efficiency. And secondly, these are the thermal characteristics as well. Sometimes the motor change the characteristics based on the thermal based on the heat or ambient heat around it, and secondly it changes based on the production. So that's why they give this tolerances. Slip, remember the slip we discussed for asynchronous motors? It is allowed to have plus minus 30% slip for less than 1 kilowatt motor, and above 1 kilowatt the slip shall not be less than 20 plus minus 20%. Lock rotor torque, the torque shall be minus 15% or plus 25% of the guaranteed torque. Lock rotor torque shall be more than 20% of the lock rotor torque. Breakdown torque shall be less than the guaranteed torque. Guaranteed torque if the breakdown torque is greater than 1.5 times the full load torque. So these are the characteristics given by the motor by the IEC standard, which motor manufacturers must follow. Then the most important ones, the ones which are related to our day-to-day life with the motor, is electrical tolerances. For electrical tolerances, IEC standard define two zones, zone A and zone B. Now zone A and zone B is zone A, the tight zone, or the small zone, or the zone in which you do not have a capacity of having too much error, which says that you can have a difference of efficiency difference of frequency plus minus 2%, which is minus 0.98, you can go plus 1.02. The motor will not have any effect on its life or on its operation or on its kilowatt. Similarly, in zone A, you can go plus 5% on the voltage and minus 5% of the voltage. So this is a zone A tolerances. Now some manufacturers also make zone B motors. Zone B motors mean that you can go 10% plus 10% minus on voltage. That means you can have more area of error or more area of flexibility, and plus minus 5% of frequency and plus 3% of frequency. So you have a bigger area under this graph, and you have a bigger area of error in zone B. For sure, zone B motors will be more expensive than zone A motors, and if you are using a motor for example in Riyadh, the voltage and frequency is very much stable because of Saudi Electric Company. They are making sure that the voltage and frequency is not going above this range. So if you are installing a motor inside Riyadh in maybe a very good location, you can go with zone A. It is not a big problem. But if you are installing a motor and a pump in a remote location where the voltage and current and frequency is not stable, then it's better to go with zone B. And for fire application, it is always recommended to go for zone B motors. So this is the difference in defining what is the electrical tolerances of the motor. Again, output current is also defined. It should be able to take 1.5 times the rated current for 2 minutes. That means a motor shall be capable of running while it is taking 1.5 times the rated current for at least 2 minutes. Then if it burns, it's okay, but the motor should have the capability to withstand or to this much current. Maximum torque, it should be able to withstand 60% higher torque than full load torque for 15 seconds. These numbers are also helpful when you are making the protection unit for the motors, because these protection units of the motors are also designed based on the very same principle, that if your motor is IEC motor, if your overload current should not go above 1.5 times for more than 2 minutes, or you should trip as fast as possible, less than 2 minutes if your motor current is going above 0.5 is at 1.5 times. So this is how the electric motor protection is made. High voltage test, you need to do the high voltage test, which is 1000 volts for rated 1 minute, and the ground test you need to do. Now this is a very small comparison between IEC and NEMA motor. Now in IEC motor, power is defined as kilowatt. In NEMA motor, power is defined as horsepower. Voltage is defined as zone A and zone B, 5 and 10, whereas in NEMA there's only one 10 horse plus minus 10%. You don't have zone A. Frequency is plus minus 2 plus 3 minus 5. NEMA have plus minus 5 by default, they do not have zone. Service factor is not defined. That means service factor says that every NEMA motor should be able to give 1.15 times more power than defined. That means that every NEMA motor is by default 15% higher or 15% bigger than the kilowatt. For example, it is saying 1 horsepower. So it is 15% bigger than 1 horsepower on, if it is saying 1 horsepower on motor nameplate. Whereas in IEC, if it is saying 1 horsepower, then it is 1 horsepower. There is no extra in it. So if you are buying NEMA motor, you don't need to oversize anything else. But by default, human have a nature of oversizing anything. So you are oversizing on oversizing. Efficiency classes, we have IE5 to IE1 to IE5. In NEMA, we have only 2 efficiency classes, NEMA Energy Efficient and NEMA Premium. Terminal blocks is standard on the top, which is this. In this one, on the side, which is on the left. Frame size in millimeter, frame size is inches. Mounting positions are defined IM3601. This is IMB14. So these are the differences between NEMA and IEC motors. Not a very big difference, but on overall, I would say that NEMA motors are bigger and bulkier motors than IEC motors. Now how the differentiation, how the change in the electric voltage and frequency will affect on the motor. So if you say this is the motor designed point, if you go 10% higher, that means your power factor will drop a lot, which is a big problem. Your efficiency will drop, your current will increase, and starting ampere and starting torque will increase high. And even if you go 10% down, your starting torque will decrease, starting ampere will increase, your efficiency will decrease, power factor will increase, and full load amperes will also increase. So that means a lot of differences will happen if you go up and down on the frequency or the voltage. Now how the efficiencies are calculated? Efficiencies are calculated based on the power output over power input. Now in motors, they are stator winding losses. That means the losses which are happening on the current which is passing through the stator, because as I said, there will be a lot of current which is passing through the stator. So all the losses which is happening in the based on the current, it will be happening here. And this is the majority. Rotor winding losses, the losses which will happen because of the rotor, friction losses because of the bearings and the frictions and the heat, iron and the stray losses. So these are all the losses which we have. Based on the standard, all the motors up to 45 kilowatt must be tested with the real load. So you need to connect it to a real load, run it and see how much power, and then divide P2 by P1. So you can say up to 45 kilowatt, the efficiencies mentioned on the motors are sort of a real efficiencies. But above 45 kilowatt, what we have to do? We have to use the formula. So we will combine, the P1 is very simple. You can get it for formula under 3 UI cos theta. So by this formula, current, voltage and power factor, you will know what is the power. then you will again the same P1, then you will calculate this, calculate all of this based on the current, temperature, and then you will document the efficiency if it is above 45 kilowatt. This is as per the standard IEC 60034. Then IEC 60034 standard also talk about how to mark your efficiency based on the efficiency point. Now for 4-pole motor, output kilowatt of, for example, 7.5 kilowatt, if your efficiency is, for example, 90, that means 90 is here, it will come as IE2. So these are the limits are given by IEC 60034, and the markings which you see IE2, IE3, IE4 are defined in this 30-1. Now in 2016 IEC defined IE5 also and removed IE1. That means as per IEC there will be no IE1 motor produced and will not be complying to IEC standard at all. You can produce it, but it will not be complying to IEC standard. And IE5 is introduced, and permanent magnet motors are also introduced in IEC 60034. That means that the motors which are synchronous and having a permanent magnet inside the rotor are also introduced, which was not earlier. And again the same thing, you can, the limits are there. If your motor kilowatt is for example 15, and you say you are above 94, that means you are IE5. So this is how you are defining how it is defined for how efficiencies limits are defined by IEC 60034 30-2. Now efficiencies vary on the different parameters. That means if the kilowatt changes, efficiency markings will change. So different kilowatts have different markings. Number of poles have different markings, different limits. Frequency have different limits. That means that if you see 400, 690, 380, at 380 volt this motor is IE2, whereas 400 volts this motor is IE3. 460 volts this motor is IE3, but 380 volts this motor is IE2. That means the motor changes on several parameters. You need to be very careful while selecting or purchasing a motor, that if you say IE3 that at 380 volts, that means it should be 380 volts 60 hertz IE3, not like if you say IE3 motor at 60 hertz. This motor is actually IE3 at 60 hertz, but this is IE3 at 460 volts, not 380 volts. So there is a difference. So these are the differences which are there. Then degree of protection. Now degree of protection is about how well the motor internal part is protected against the dust part and the water. This is for all electronic and electrical equipment, even for your mobile phones. 0 means no protection. 1 means more than 55 millimeter cannot go inside, like a hand. If the motor have these two digits, dust and liquid, 0, 1 here, that means a hand cannot go inside, but a finger will go inside. The same goes like if you have 4, then wires will not go inside, but a smaller thing than 1 millimeter will go inside, like dust. If we have 5, that means dust will not go inside. If we have 6, that means completely dust proof. For water, we have 0 means there is no protection. 4 means water splashing for every direction. 5 means water projected from a nozzle from every, that means with some pressure. And 6 means that high pressure. 7 means that it is submerged. That means IP67 will be submerged. Usually the motors which we use by standards are IP54 or 55. These are the standard surface motors we use as per IEC motors, as per IEC standards. and these motors are good for pump rooms and will work most of the time, and are dust proof and have water splashing from any direction or water with nozzle. But it is not advisable to throw these pumps inside water or a swimming pool. It will not work after. So it's it's just, you need to make sure that that you are giving you are not taking a pipe of the water and start cleaning the motor with the water. It probably will go inside if the water is with very high pressure and the IP is 54 or 55. Then there are three methods of cooling. The three methods for IC 410 is there is no forced cooling or fan. So the motor is just there with the ambient amount with the ambient cooling. It will be cool itself. So it will be cooling itself. So this kind of a motor is used in cold areas. Why? Because why it is used in cold areas? Because the cold air in the environment will cool down the motor. But if we are living in a hot region, what we need to do, we need to have an additional fan installed to the motor, and this is what you can see in our example. This is the fan which is installed to the shaft of the pump. Once the motor is operating, this fan will also be operating, and this fan will give the cooling air. This fan will throw the cooled air to the motor. Now this is called IC 411, and in this one, motor is cooled by the load attached to the motor. In IC 418, the motor is cooled but not with the fan attached to it. It is forced convection. That means someone is throwing the water, or some media is cooling the water. So that means there is a cooling mechanism, but that cooling mechanism is not driven by the motor. This is usually happen in submersible pumps, this bore well pumps. The cooling of the motor is not given by a fan, but it is given by a flow of water. Because if you know, this is the borehole and this is the motor of the submersible pump, this is the suction, and this is the impellers, different impellers. Sorry, I put it wrong. This is the motor of the impeller, and this is the different impellers. The water will come here, go through all of the motor, cool it down, and leave the pump and leave out. So all the water is cooling the motor, but it is not, the water is not, or the cooling is not done through a fan attached to it. It is done through the motion of the water around the motor casing. So this is called IC 418. Then there is something called frame size. Frame size is very simple. Frame size is the distance between the center of the shaft to the base of the pump. The base of the motor. Now this distance in millimeter is defined as the frame size of the motor. 90, see this is B3. So 90 is 90, 100, 100, 160L, 160M. So something called medium large. So there are two things, medium and large. So then we'll have two different sizes. Why we have to define the size? Because of this. We have to define the size because in frame size 56, that means when we have this B3 distance of 56, we can have only 2 kilowatts in this size, 0.09 and 0.12. But if we have, for example, 132S, then we have again, that means that B3 size is 132 millimeter, and then you can have 5.5 kilowatt and 7.5 kilowatt motor in this, in 2-pole. In 4-pole, 5.5 only, because you know why? We will have a lot of magnets inside it and will not have enough space. So these frame sizes are defined as the distance between the center of the shaft to the base of the motor. Mounting arrangements, this is foot mounted. That means you have a foot with the motor. Motor with the tapped holes. You have a tapping holes below the motors here. So you will attach it to the load directly. Then you have a flange. You will have a load and you will attach the motor attached to the flange. And then you have a flange and the foot. They are flange and the foot usually defined at B35. This one is B5, V1. Why this is B5 and V1? Because it could be horizontal, it could be vertical. The same thing, B14, V18, it could be horizontal, it could be vertical. V for vertical and B14 for horizontal. And this one is always horizontal, and this one is always horizontal because we have the foot for it. Then direction of rotation, it is mandatory by the standard to write the direction of rotations and the connection marks, which is this star or delta. I will come to that, what is star and what is delta. Now if you see a motor nameplate, you will find something interesting, that the same voltage, same motor is mentioned to have 220 volts and 380 volts. How come it is possible to connect the same motor, because this nameplate is for the same motor which is 1.5 kilowatt, to have two different voltages, or even if in this case is 380 and 660? How come it is possible to have the same motor but with two different voltages? Now this is possible with the way the motor is constructed. If you see the motor have, just a second, the motor have this terminal box. Now this terminal box is where you will bring and connect your three phases: phase 1, phase 2 and phase 3. And if you see here, there are actually 6 connections: 1 2 3 4 5 6. Why we have 6 connections? Because we have 3 windings inside of the motor: winding 1, winding 2, winding 3. Because of the 3 windings of the motors, we have 2 ends of the cable. If you see, red and red, yellow and yellow, blue and blue. So blue and blue is one winding which is going inside the motor, and it is generating a magnet because of the rotation of the cable, because of the current going through winding, which will generate an electromagnet. This 3 will generate 3 magnets. Now the way we connect them, if we connect them in star, which means that we will have a common connection in between them, then what we will have, we'll have 2 resistance in our path. That means the current will enter through here. See, the current will enter through here, will pass through resistance 1 and will pass through resistance 2 and will go out. Or you can say this is how the path of the current. You have 2 resistance. That means that in star connection, which is this connection, because of the 2 resistance, a higher resistance, you need more voltage to generate the same electromagnetism, or the same magnetism, to power 1.5 kilowatt. But in delta connection, in which what we do, rather than having the same strip here, we will have one strip here, one strip here and one strip here in real life connection. What we will do, we will connect it in this way, and now the current will go through only one resistance. That means your resistance is less now. Once the resistance is less, your current will be more, and your magnetism which will be generated will be more. Because of that, your delta voltage will be less. So just with the change of how we are going to connect the motor, either we are going to connect the star or we are going to connect to the delta, we can change how what is the voltage required, or what is the voltage you can connect to. Now will the parameters will change? No, the parameters will not change. For example, if you connect the motor in delta like this is delta connection, sorry, this is star connection. If you connect the motor in star connection like this, so, and you connect the motor to 380 volts, all the parameters will remain same. Like it will still give 1.5 kilowatt, it will still consume this 3.3 ampere, which is adjacent. So this ampere is for 380 volts, this ampere is for 480 volts, this ampere is for 277, this ampere for this. And then efficiency, the speed will remain same, the poles will remain same, the efficiency will be different on all the voltages, but the major, see over here, if you can see, the efficiency is different, but the major characteristics, the power which the motor can give, will remain same. It does not depend either you connect to star or you connect to delta. But what is the most important thing is you connect based on your site voltage. For example, the site voltage you have is 380 volts. So what connection you should connect to? The same motor to star. So this is the connection you should use if you have 380. But if the same motor you want to connect it to 230 volts, three phase. So what you need to do, you need to connect it to delta. The same motor will work in two different voltages, giving the same characteristics. But for example, if your site voltage is 380 and you connect it to this 220, what will happen? The motor will run but very slowly. The rotation will reduce drastically. But if you sorry, I did otherwise. If you connect 380 to 220, the motor will burn. There will be no rotation at all. No rotation at all. So your motor will immediately burn. But if your motor is 230 volts and you connect it to 380, what will happen? The motor will rotate but slowly. Why? Because the magnetic field which is generated by 230 volt is very less, and it is not able to go up to 1.5 kilowatt and this speed. So it will run, but it will run very slow. So you can connect 230 to 380 volts. Motor will not run, or motor will not burn immediately. It will burn after maybe very long time, but it will run slowly. But if you connect 380 volts to 220 volts, that means 380 volt and you connect it in delta, it will burn immediately. So this was star delta concept. Now thermal protection. The motors are usually with thermal protections. These are the PTCs, TP111, TP112. It all depends. The first letter is for only slow, slow fast, or only fast. Types of protection. Only slow mean if it is slowly overloading, it will trip. Fast mean it is stalled, suddenly stop because of something, it will trip immediately. Cutoff level 1 or 2, it depends on the type of protection provided inside the pump. Vibrations. How much vibration is allowed? This is also defined in IEC 60034-14, saying that two grades, vibration grade A and vibration grade B. A means that from frame size 56 to 132, vibration suspended. If the motor is suspended, that means not rigidly mounted. This is all the values which are allowed. For rigid mounting, this is allowed. For B, suspended is allowed in this 11, and rigid mounting, no vibration is allowed. That means vibration grade B is a more strict grade. So if you are in a scenario where you want to buy a motor with no vibration at all, or a minimum possible vibration, rather than mentioning how much vibration you need, just mention I need grade B vibration for IEC 60034-14. By default, you will get the minimum possible vibration for that frame size. So this is how the standards help you to streamline your procurement or your motors or the manufacturers. Now, one most important thing, electrical insulation. Electrical insulation is a term which helps to understand how much internal temperature is allowed. Now, to understand this, it is very important to understand where it is applicable. If you know from the previous one that this winding is the winding which will help us to make the magnet in the stator. Now, if the current is flowing through it, that means that one current is this cable is insulated from this cable. This cable is insulated from this cable. Now there is an insulation material between these two cables. This insulation material has some capacity, because if there is no insulation material, the moment we will give the power, this will burn because of the short circuit, because this voltage, this wire is connected to this wire. But eventually these are not connected. This is a small, very thin layer of insulation between this wire in the stator winding. So this insulation have a capacity, or you can say have the maximum temperature which they can withstand. Now where is this winding? This winding is actually inside the motor here. That means the temperature here shall not increase these values. Now if I say my insulation class, this is the quality of the material used for insulation. Now if I use insulation class A, that means that the temperature at this point, which will include the temperature of the current going inside, the temperature from outside, the temperature because of the rotor rotating, the friction, all of the temperatures combined together, shall not increase 105. If I'm using insulation class E, it shall not increase 120. If I am using insulation class B, it shall not increase 130 for F, 155 for H, 150. In pumps, majority of the time we are using insulation class F, which means that we are allowed to have ambient temperature of 40. This will be temperature from, for example, this is my motor and this is my stator. This is the ambient temperature of outside, the air. 105 is the temperature permissible rise. This is the temperature rise inside the motor, which is all the motor, because of the winding, because of the resistance of the rotation, because of the sound, whatever, all the heat generated inside the motor must not increase 105, and then this 10 degrees is the margin. Now understanding this, how it works, what I can reduce here. If I want to reduce, what I can reduce? Ambient, I cannot increase, I cannot reduce. It depends on what is the ambient temperature outside, what is the weather outside, where it is installed, what is the application. So this I cannot reduce. Permissible temperature, how I can reduce this? I can reduce this by using a better copper cable. So if I use a very good copper cable, what will happen? My heat generation, the heat generation formula is I square R. This is the heat generation, the current and the resistance. What I do, I reduce the resistance. What will happen? My heat generation will reduce. Once the heat generation reduces, my permissible temperature reduces. So this is what I want to make sure, that I have to use a copper cable so that my permissible temperature shall not increase 105 if I am using what? 155 degree insulation class. But what will happen if we have more than 40 degrees centigrade? Some places like Saudi Arabia, we have 50 degrees sometimes. So how we can make sure that we have a motor for 50 degrees? For this reason, we use another concept. We use a concept called insulation class F and temperature rise B. It is written like this, for if you can see here, like this. Sometimes it is written like 155F to 130B. What is the meaning of this is, the motor which I am using, or which the datasheet you are referring, is using insulation class F, which can withstand 155 temperature. But B means, this B means here, the temperature rise is not 105, but the temperature rise is 80 for insulation class B. That means how much extra I get? 25 degrees. So how I will distribute this extra 25 degrees? I will do this 60. This is already 80. Why? How I made this 80? Because this insulation, this material I use is very good quality, that the internal temperature and the heat sinks, because how the internal temperature rise is known, because of the heat sinks is very good, because of the area is very good, the motor is cooled very properly. That means that my internal temperature will never go above 80. So I give this 60 and I make this 15. So now my motor can go up to 60 degrees with even insulation class F. How? By improving the internal temperature rise. Now my internal temperature rise is not going to 105. Now it is going to 80 degrees. That's how, or this is the meaning of insulation class F to B, or something which is written like this. Now if sometimes you need to derate it even further, sometimes you need to make sure you are using a motor with VFD. With VFDs, this concept does not work. F to B does not work, because VFD, the waveform is not very simple. The waveform is a lot of variation is here. Because of this, it generates generates more heat. So this 25 degrees will eventually go to the heat generation in this. So for if you're using a motor with VFD and you need to derate it to 50 degrees or to 55 degrees, you need to increase the power by 10% or 1 minus derating power or higher altitudes. So this is how it will improve, or you need to derate in case you are using higher ambient temperature or higher altitudes. This is F2B insulation class. Approvals and markings. Once you will receive a motor, if it has CE mark, that means this is applicable to all IEC 60034 standards. Or if you have CURUS mark, that means it is a NEMA motor applicable or complying to NEMA standards. Now coming to the last topic of today, which is motor protection. I apologize, it is getting long. Will just take another 10 minutes, but let's do it. So motor protection is about how to protect the motor. Now why we need to protect the motor? The first and the foremost important thing is overload of the motor. Overload is something which is in our control. It is not in the nature control. Overload is happening because the load on the motor is more than what it is designed for, and we failed to stop the motor before it burned. So the 30% of overall motor failures are because of the overload. That means we can save up to 30% of the motors just by designing a better system. Now there are three ways of protection of motor. The first one is built-in, then overload, circuit breaker, and fuse, and I will go one by one through all of them. So the problem with motors, what kind of faults we get: over voltage, under voltage, imbalance voltage, frequency. All of this is related to the power failure. Then sometimes what happens is installation is not done properly, or sometimes slow developing temperature rise. These will be high developing or fast developing temperature rise. This will be slow developing temperature rise. Like your motor is developing the high temperature but very slowly. For example, your ambient temperature is high, but it will not burn your motor instantaneously. It will burn your motor after some time. Or high altitude, you don't have enough oxygen to cool down the motor. Or high liquid temperature, because the liquid is going till this point here. So the liquid is, for example, 150 degrees centigrade. All the pump is designed for only 110 degrees centigrade. What will happen? This additional higher temperature will go through the shaft to the motor, which will again overheat the motor. Or frequent start and stop. You are starting and stopping the pump very frequently. This will also increase the heat of the motor. Or quick developing temperature rise. Sometimes the quick developing a lock rotor, motor was rotating and suddenly something stuck inside the pump. The motor stopped and motor is trying to rotate, but nothing is happening. It will suddenly increase the temperature rise. Or something called phase breakage. Phase breakage means you have line 1, line 2, line 3 given to the motor, and suddenly one phase is not there. If this situation comes that you have only two phases, these two phases will overload significantly, that it will burn very fast within a split of seconds. Now for these things we give fuse protection. Fuse protections are quick acting fuses. So what it does, it is given for fuses are given for short circuit protections. Why? Because in short circuit protections we have a very high current for a very short period of time. For that reason, this is called inverse time curve. That means that 1 is the rated current. Over here nothing should happen. This is the part where the motor should run all the time. But above this, if it goes 6 times the rated current, that means it will take 0.7 seconds to trip the system. If it goes to 10 times the rated current, it will just take 0.2 seconds to trip the system before it actually damages the pump. So this is how the fuse works. So greater the current, shorter the time it will take. Then there is something called time lag fuse. Time lag fuses is this black one, which will give some more time, or you can say more time here, if your current is more than 1. So if you see here at 1, nothing is happening. So there is no problem if you are running at full load current. But if you go more than full load current, suddenly you will trip. Circuit breakers are overcurrent devices. The fuses which we discussed earlier was for current which will go for short circuit. That means very high current for a very short period of time. Circuit breakers are used for slow overloading. Slow overloading means that you are improving your motor is overloading. That means it is taking a little bit more than a rated current, but not too much that it will trip. So there are two kind of thermal circuit breakers. One is thermal, one is magnetic, and nowadays there is something new called thermal magnetic, which is a combination of both, because one have some benefits and other have some benefits. The thermal magnetic have the benefits of both. Thermal are temperature sensitive. That means very slow overloading, it will increase the temperature and it will trip. This is not voltage sensitive. On the other hand, magnetic is not temperature sensitive. For example, at a very high ambient temperature, this will trip, but magnetic will not trip. But the magnetic is voltage sensitive. For example, just a voltage spike will come, it will trip. Fixed time delays, various time delays, push to reset, switch functions, small packet size, lower cost. This is a higher cost. So there are few benefits and few drawbacks. This is the curve. If you see here, if this pump is working for very long period of time at rated current, nothing will happen. But if it run for 20 minutes, or if you remember I said 2 minutes or 1.5 times, then it will trip within 2 minutes. So that is the reason these kind of pumps, overloading IEC pumps, are using class 10 trip type class 10. Why? Because it will trip faster. For NEMA motors, because NEMA motors are designed with more flexibility, you can commonly use class 20 breakers. So class 20 breakers will take even more time, because if the same current was taking a NEMA motor, it will take 3 minutes rather than 2 minutes. So this is the difference between IEC motor and a NEMA motor. So this is the combination of all the fuses. So this was the full load current, which is taken in the very beginning. This is the motor, this is the starting current, and then the motor goes to the full load current, which is throughout it will operate. This is the overload current, overload relay. So this, whenever it will go here, this will trip, but if it goes suddenly very high, then a fuse will break. So typically all of these protections are given to the motor. These fuses are giving short circuit protection. This thermal or this TM or this thermal magnetic overloads are giving slow overload protection. So the motor is protected usually usually for all of this. But what will happen if you design your thermal magnetic very high? For example, the rated current was 5 ampere, and the rated current at which this will trip is 10 ampere. What will happen? Something will happen which is not good, which is that at 7.5 ampere, which is more than this will consider that this is okay. That the thermal magnetic overload relay will not consider it as wrong, whereas motor is overloading already. So usually the bigger is better does not apply here. You have to size your overload exactly as per your motor overload current, motor rated current. So if you oversize it, it will not give any protection to your motor. So you need to make sure that your overload current is exactly sized. For example, this is 5 ampere, then this overload should be at 5 ampere, so that this knows that the rated current is 5 ampere and I'm going more than 5 ampere. Then we have some electronic motor protections. This kind of devices give all of this protection in one device. This is usually used for high sensitive equipment which are used in industry, or equipment which needs a lot of protection. Then we have some built-in protections, thermal switches. This kind of clicks and this kind of thermal switches are installed inside the windings. These are just on off switch. That means that it have a nominal temperature. Whenever this temperature will come, the switch will open. That's it. Or you will go to very high resistance, which is open. So this is just on and off. Then we have PTCs. PTCs are the devices which are thermistors, which means that it changes the resistance based on the temperature. So these are called thermistors. PTCs are positive thermistor temperature coefficient. That means the resistance will increase with the increase in temperature. We have also NTCs. That means that the resistance will decrease with the increase in temperature. And then how you will know what is the nominal temperature? You will know this by the color of the cable. So if you have blue red means that you have 160-degree nominal temperature. If you have black and white, you have 145. Just by knowing the temperature, knowing the color of the thermocouples which are coming outside of this terminal box, you will know what is the tripping point of your motor. Usually we have 3 PTCs distributed at 120 degrees to each other in the motor windings. Now this is how resistance is there. The nominal resistance is this, minimum is this, reference is this. That means at this point this is slow overloading. With PTCs, the good thing is that you can understand the motor is slow overloading. But with Clixon, the one which is on and off, you cannot know this is slow overloading, because it is just either no resistance or either full resistance. In this one, you have the change in resistance, which can tell you that the motor is slowly overloading. Then we have PT100. These kind of sensors are used in devices where we really need to have very accurate control. In this one, you have on 0 degrees, you have 100 ohms. And as you go further, you will get a specific ohm. That means at any given point, if you measure the resistance, you will know what is the actual temperature. Actual mean in the figures. 110 or 120, so you can design your own protection system based on the values coming out of this. So this will really help. Then this is the motor curve. The motor curve is a very simple curve which talk about 0 to 100% of the speed. In the very beginning, we have a very high torque, very low lock rotor torque. That means we need to give, remember, torque was the force. What was torque? Torque was the radius into force. We need to give very high force, turning force or twisting force. In motors we say twisting force to start the motor. And then we have pull-up torque. Then we have breakdown torque. Breakdown torque means that after this torque, the motor will be finished, will be broken already. And then we have full load torque. This is the torque at which will be giving the required kilowatt at the required speed. This is the full load torque. The number of start and stops are limited. You cannot have 500 start and stops. It depends on the motor kilowatt and the motor manufacturer. Why we have a problem? Because whenever we run the motor, we have to overcome lock rotor torque. Lock rotor torque means if my motor starting current is if my motor rated current is 100 ampere, my motor starting current, this is my rated current, my starting current will be somewhere between 500 to 700 ampere for a very short period of time, but it will consume this much current. So once it will consume this much current, what it will do, it will overheat the motor. If you do this maybe 30 times per hour, that means you might burn your motor by frequent start and stop. So what we need to make sure that it depends on the motor kilowatt. Sometimes some motors can go up to 120 or 500 start and stop per hours, the smaller ones. But for some motors, it depends. So you need to always refer to the manufacturer what are the number of start and stop of any given motor. So when you design a motor, or when you buy a pump, all of the matching of the torque and how much kilowatt, this will be done by the by the software itself. You really don't need to go and do the matching yourself and select the motor, the type S1, and the lock rotor torque, how much it will be, how much it will be at full load and no load. You don't need to do that. All this will be done by the motor or the pump manufacturer for you. Now, once we start the motor, as I said just now, once we start the motor, it takes 5 to 6 times or 500 to 600% the rated current, which is not good for your motor or your system, because this current will be coming from Saudi Electric Company or from generator, and whenever you turn on the motor, it will consume a lot of, or it will suck a lot of current from the system. So how we can reduce this? To reduce this, we have something called starting methods. Starting methods, what it do, it helps us to reduce the starting current from somewhere 500 to 600 to 100 to 200 to 300, or sometimes even below 100. So there are few ways which can help us to do that. The first one is direct online. This is not a starting method. This is just you give all the voltage to the motor. You give it in one shot, and the starting voltage is the starting current is from 500, between 500 and 600. So this is the very basics starting method, DOL, in which you are just giving the motor the voltage without any reduction. The other one is star delta. In star delta, you remember I said just now that if your voltage is 220 site voltage, okay, and you connect it to 380 star, what will happen? Your motor will slowly revolve. In star delta starting method, we use the same concept, that if our site voltage is 220 and we first connect it in star, what will happen? It will slowly start rotating. After few seconds, when it will slowly rotate, we will convert from star connection to delta connection. To do this, what is required at delta connection? 220 volt, it will go to full speed. How this will help us? The initial torque which we need to give now is reduced. With the help of this, what we can do, we can reduce our initial torque, current from somewhere 225 to now 75. You can see there is a big spike here, but this big spike is a very small period of time compared to the period of time this. If we use DOL, the short circuit, the full load torque will be for this period of time. But in star delta, the spike is there, but for very short period of time. For this reason, we used to have 3 contactors. The star contactor will close, giving it a common point, so the motor is in star connection. After that, this will open and this will close, giving it delta connection. So the same motor having 6 leads is now, because this is the 6 leads, 1 2 3 4 5 6, is first connected to star and then connected to delta. But now question comes here. For example, if you have 380 volts for this motor, can you do this? No, you cannot do this. The rule of thumb is, to do the star delta connection, your site voltage must be in delta. What is delta here? 220 to 277. You cannot do this. This is 380. For this, we need to use other motor. In this one, what is our delta? 380 to 415. And what is our star? 660. Now, in this case, if our delta is 380, and if I connect it into a star, because this is star, what is the required? 660. But what I am giving? 380. What will happen? The motor will slowly rotate. But after some time, 1 or 2 or 3 seconds, once I will change to delta, once I will change to this connection, delta connection, in this delta connection, what is required? 380, and I'm giving it to 380, it will go to full speed 100% immediately. Where all of this is happening? All of this is happening inside this 6 connectors. 1 2 3 4 5 6. If you connect it in delta, something else will happen. If you connect it to star, something else will happen. Are you doing it manually? No, you are not doing it manually. It is done with the help of these contactors, these electrical devices, which will help to give the, like electrical switches. They do this job automatically. So first, when you click this green button, what will happen? K1, this contactor, and K3 will close. What will happen? 380 we will connect in star. More voltage was required more, but you are giving less voltage. Motor will slowly rotate. After 3 or 4 seconds, K3 will open, K2 will close. What is required? 380, you are giving 380, it will go to 100% speed. So that's how star delta starter work. Some real life example. This was the motor which was rated, which rated current was somewhere around 30 ampere, and in DOL starting, when you start the motor, you goes up to 120 ampere for this much period of time. But in star delta starter, once you connect it into delta, you goes from 30 to 70 ampere, and for a very short period of time you go up to 120 ampere. So this is how star delta helps. There is something called star delta closed transition. Closed transition, star delta is also another type of star delta which will also reduce this transition, but that might, you can look it up you can look it up. I did not include this here because it's a lot of control, but you can look it up, star delta closed transition. So you can even avoid these spikes from here. Then we have an electronic device. This electronic device is something called soft starter. This electronic device will start the motor with a very low speed and then increase the speed to the 100. So when it will start with a low speed, what will happen? The starting torque will be low, and then the current will not go to the full load torque or the breakdown torque. It will go a little bit above, which is around 110% only, and come back to a normal. So soft starters are electronic devices to do the same thing. It changes the speed from 0 to 100%. Then another device is frequency converter, variable frequency drive. In this one, the good thing is just work like, for starting, it just work exactly like soft starter, which means that from 0 to 100 it will go from take 600 times. It will just take this much current, which will go up to 175% of the full load and come here. But the good thing is that during the operation you can change the speed anytime you want, between 20% to 100%. So if your demand change, you can change the speed. So not only you will reduce your starting current, you will also reduce your energy consumption based on your demand. And the good thing is that based on the affinity law, you can change the flow and head whenever you are required. So frequency converter is something which is used majority of the time in commercial applications, and this is something which is required to have in applications where your demand is changing. So if the people are using the water, in the morning they're using more water, in the evening they are using less water. So probably frequency converter is a device which will help you to do these changes. This is how the frequency converter work. I will not go into the detail, but the input filters, this is the supply coming, the rectifier, we will make it DC, we will store it. This is the DC here rectifier. We will make our own AC again, and our own AC will look like this. So the mains are very good smooth vanes, whereas our DC will not be very smooth based on the rectifiers. Because of this, we have some limitations now. If we have more distance between VFD and the motor, we need to use some filters to avoid this too many variations or spikes. So what these filters do, you give this input to the filter, it gives a very smooth very smooth output to them. So they are du by dt filters or sine wave filters. So there are two kind of filters to do this. Now what happens also, because of the using of variable frequency drive, we tend to have the currents generated inside the bearings. So this is the first loop, this green loop, and this is another loop, and then there is a bigger loop of the current which start going inside it. Because of this loop, the chattering happens inside the motor in these bearings, and because of this, after some time, what you will see, your bearings fails. Why this is happening? This is happening because a lot of spikes all around it and a current increasing, a very high current. So if this current is low, it is okay, but if the current goes very high, then this start creating problem for the bearing of the motor. To avoid this, what we use hybrid bearings or a ceramic bearings. We try to close or cancel this flow of current or this circuit. How? There is a bearing here. If you see here in this motor, I have two bearings. This is my bearing 1, and this is my bearing number 2. Now the current will start flowing between this bearing, between this metallic enclosure, and start coming back. To finish this, to stop or disconnect this circuit, what I need to do, I will just simply use this bearing not made of metal. So this bearing, this ball will be of ceramic. This will be steel, but this will be of ceramic. So the current will come till here, but will not be able to pass through it. So, or I will use insulated bearings, either ball insulated or either this complete shell insulated. This is also possible. The current will come but will not pass through it. This is called insulated bearings. Now the question is when to use them. The rule is like this: if your motor frame size is less than 225 frame and cable length is less than 25, cable length means the length between VFD and the motor is less than 25 meter, then neither insulated bearings are required nor sine wave filter is required. Nothing is required. Just connect it and operate. But if frame size is less but the distance between cable is more than 25, then insulated bearings are not required, but sine wave filter is required. And if frame size is more than 225 frame and the cable length is less, insulated bearing is recommended. Remember I said in this picture that we need to disconnect this circuit, and if the current is more, then it will create a problem. When the current is more, when the size of the motor is big. So at 225 frame or bigger, even the size is smaller than 25 meter, insulated bearings are recommended. And if the frame size is big and the distance is big, both are recommended, insulated bearing and sine wave filter. So this is the rule of thumb, not mandatory. It's always good to have insulated bearing and sine wave filter, but it's always economical to it's always good to find an economical balance between a good to have and must to have. Then there is something called reinforced insulation. You can also purchase a motor with having more insulation. What is reinforced insulation? This winding which you see here, this will come with more material and more paper inside and more insulation material inside, just to make sure that your winding, you have a more thicker layer of winding. This is called reinforced insulation. This is also possible, but this is used in very high, very big systems. This is how it looks like for reinforcement. Now comparing star delta and comparing different starting methods, DOL is the cheapest, star delta the second, soft starter is the third, VFD is the most expensive one. But the starting method here goes up to 10 times the lock rotor current. From here 2 to 3 times, 4 to 5, over here equal to IR. So VFD starting current is equal to the rated current. So your starting current will be very low. Voltage dip, the voltage dip is when you start the motor, suddenly there is a voltage dip in the system. It's very high, in this one very low. Power factor is very low in DOL. But power factor, because we have this DC system now, we have a high power factor. So higher the power factor, it is good for the system. Number of start and stops, it is restricted. But in VFD, you can have a very high start and stops. With the same motor, you can have more than 50 start and stops if it is have a VFD. This thermal stress is very high. In VFD, thermal stress is very low. Mechanical shocks is very high. In VFD, mechanical shocks is very low. So this was it from my side. Thank you very much. I really apologize for this very long. I took approximately 1 hour more. I think it was worth it. You will get all the recording. You can go through it in your free time. And I will go through the questions once again. We are all facing quotation when. Can you explain us about the poles? Okay, from where the question started. Okay, why sometimes we see air motors it stop by brake, and who can keep induction motors work as generators? Why match the kilowatt? Brakes are usually required, and induction motors can work as generators, and it will work as generators. That's why sometimes the resistors are used. How it will work as generator? Because when the rotor is made of magnet. If the rotor is not made of magnet, it will work as a generator for a very short period of time, and then it will not work as a magnet. As you know, we have more hard. Some motors not have a thermal protection. How can we add it? See, once the motor is produced, you cannot add a motor protection again. That is impossible, because more thermal protection is inside the winding. You cannot have it. But what you can do, you can install more sophisticated motor protection unit, like electronic motor protection unit, to give more protection. If you really want to add thermal protection, you can add thermal protection on the motor casings or motor bearings. On bearings it is possible to add thermal protection, but winding it is not possible. What about the magnetic concept of train running by it? So the train is using, I'm not the expert of the train, but I can say the train is using leviation, and it is very similar. The electromagnetic induction is very exactly same as motors as in trains. So they do make the electromagnet. Can you explain us the poles? Number of poles is like magnets inside the motor. The more magnets mean more power to lift up the things, but slowly. And poles reduce the speed of the motor. Power factor is more important issue when selecting the motor. All company not same. Who can provide power factor? 1 phase, 3 phase. Who we can improve? See, to improve power factors, one thing which is used on site is usually capacitor banks. With use of a capacitor bank, you can use the use of the capacitor banks. You can improve the power factor. So power factor is possible to improve, but not after the motor is produced. If you want to improve the power factor while the operation, you need to increase the power factor bank or the VFD. Both will help. All time we are facing quotation. We can running 50 Hz pump by 60 Hz source or 60 Hz motor by. See, you can run 60 Hz pump on 50 Hz. You can run 60 Hz pump on 50 Hz. It will work based on the load. But if you run 50 Hz pump on 60 Hz, this will be a big problem, because once you will increase the speed, the load will increase, and once the load will increase, your motor will burn. So what you need to do, You can run the 50 hertz 60 hertz pump on 50 hertz, but it will not give the same output. It will give the reduced output. This I'm talking about the pumps. I'm not sure about other equipment, but yes, for the pumps you can work for 60 hertz pump on 50 hertz pump, but never ever work 50 hertz pump on 60 hertz pump. It will burn very quickly. Yes, you can get the video. Servo motor, if we get any reason, who can protect it and drive? Thank you very much. If fuse not disconnected, load even its ampere, come more fuse because it's problem. Yes, you are right, my dear. I have to have a time management course. I'm sorry for this. I'm sorry for this. Thank God I was not fasting. It was not in while fasting time. Is there any equivalence of IC standard for NEMA design for motor A, B, C, D? How NEMA design plays a role in selecting our motor? NEMA designs are bigger motor. That's it. IC design are equally good, equally better. NEMA designs are bigger motor. So this one last question. RTD, when we must add it to the motor? I mean, RTD above 3.5 kilowatt, you must add it to the motor. That's it. This is the basic rule from my side. This is what we as a Grundfos also do. So, but it is up to you. Usually manufacturers above 3.5 kilowatt, they add it. If I have a pump with head pressure greater than a tank, how can I control the pump? I talked about 4 ways of controlling the pressure. The easiest way is to install the VFD. This is the very easiest way. Relay setting. Yes, you need to have the relay settings. You need to have the relay settings once you have the RTD. There are a specific RTD relays by Schneider. I don't remember the models, but you can have the RTDs and connect this to those relays, and then it will work.